So I'm not the important one.
Okay. I'll try to get it ready here.
Okay. And if you're going to put, you can mute yourself as well if you'd like. You don't have to, but.
Okay. So am I sharing the screen?
Not quite yet. Just give it a second. All right. I don't see it yet.
Okay. Come on. Choose what to share with. Window. There we go. I do hear you, yes. I don't see you though because my screen went big and now I can't see you. Okay. Okay. I can do my own intro, no problem. But do you see the screen? Do you see my presentation screen? Because I'm not able to see you or any of the chat stuff. So I all I'm seeing is my presentation screen. Okay. And we're live. Okay. Ready to start then. Okay. All right. Well, let's say good afternoon to everybody, and thank you for joining us today. So far, it's been a pretty good training from what I've seen. So glad to have everyone join. My name is Greg Kurtz, and I'm the technical director for the International Ground Source Heat Pump Association, which is located in Springfield, Illinois. And we are rolling out some new geothermal heat pump training courses for the 2024 year. And so my presentation is about 30 minutes worth, going through an overview of what we're going to be bringing out in the first of the year. And so I guess we'll get started right away. One of the things that's kind of driving electrification and heat pump interest, I guess, would be a lot of the world governments are all promoting ways to minimize climate change and trying to decarbonize our environment and get off of fossil fuels as the primary fuel choice and improve our climate. So a lot of the countries are coming up with some, incentives, such as in the U.S., the Inflation Reduction Investment Acts, and Canada, I know, have several programs as well. So the governments are kind of promoting the technologies to step forward and be more used. And so therefore, that's bringing a lot of interest to people on heat pump technology in general, whether it's air source or geothermal. And so it's just a big driver anymore. And so energy efficiency and conserving energy is really one of the best ways to help do that. And with geothermal heat pumps particularly, they're probably the best choice and have the biggest impact on reduction of carbonization. So in my presentation today, I'm going to kind of tell you just a little bit about who IGSHP is. IGSHP stands for the International Ground Source Heat Pump Association. So I'm going to cover that. I'm going to show you some of the new formats and designs that we're coming up with our newest training programs we'll be rolling out, which are formatted for expediting workforce development training. And we are, through that, building job-specific training modules, which are task-focused. And all of the training is based on ANSI CSA IGSHP-based C448 standards. So what we roll out is going to help with matching right up with all of those standards and codes. So that's a great thing that's being incorporated into the new training. These will be instructor-led, in-person or online versions of training programs. And so we're going to really roll out in our first group 3 different training programs. The first one is called the Residential Geothermal Heat Pump Systems Introduction and Overview. And that one is kind of a getting people up to speed presentation before they take an actual career trade training class, such as an installer class or a service technician training. There's a lot of people that are joining the industry maybe as a new career person, and they don't have a great background understanding of geothermal heat pump systems, how they work, their benefits, and the components that are part of the installation. So we have a preview kind of introduction overview module that will be available before the actual installer training or a service technician training class. So it's pretty flexible to help those newcomers get acclimated before we jump right into the technical materials for installing or servicing a geothermal heat pump system. And then at the end of our training courses, the students would get, on completion of an exam, passing it with a 70% completion rate, 70% passing rate, you would get the ICSPA certification of completion to go along with that as a credential to verify and back up your training knowledge that you have taken with our courses. So who is ICSPA? ICSPA is an organization that's a nonprofit-based, member-driven organization that started in 1987. And their focus has been on the ground source heat pump technology. And they have worked with a lot of local, state, national, and international level folks. So we cover, quite a amount of ground. And even internationally, we're working with other geothermal heat pump associations globally, such as in the UK and Sweden and other places. Where offices are located in Springfield, Illinois. And as you can see on the screen here, that's our address. And the benefits of being a member of ICSPA is that you have the networking capacities that our organization brings to help you learn and connect with other like-minded people that are involved in the industry. We have developed a lot of invaluable training resources and materials that have been used for years with geothermal heat pump systems. And we do a lot of the technical support side of what's related to the industry. We have a sister company, kind of, if you will, that's a nonprofit organization called the Geo Exchange Group in the U.S., and they're kind of our marketing arm here in the United States. And so we kind of work close with those also and that association. So it's kind of a sister association, but 2 different nonprofits. So getting right into the workforce development training that we are developing, our training modules that we'll be rolling out are really kind of groundbreaking. Our organization has not been able to do this before, but we have had a really good, coming together of a lot of entities in the industry with the ground source heat pump systems, such as equipment manufacturers with their technical training departments. We've got drillers and loop contractors. We've had engineering firms and consultants, trade associations, and utilities, all coming together to help us bring things to our training material that they would like to see as an industry as we roll this out and move forward. So we've had a lot of good input, and that is still going on as we finalize some of these courses and bring them to the market. So it's certainly going to be, I think, some of the best training that the industry's ever saw being rolled out. Like I said earlier, everything is based off of good standards such as CSA, and this is kind of a shot showing the design and installation manual for the CSA folks on ground source heat pump systems for commercial or residential designs. If you're not familiar with that, that's certainly a document that you're going to want to know more about, because this is what a lot of the codes are based around. And we as an organization have helped those firms write some of those design standards, which are very important, we feel, to get good design installations. When we do finalize the courses, they're going to be available on our website at www.icspa.org. If you go to our website to the training link, you'll be able to find them, as we have our current products on there now. So this is just a screenshot showing you where to locate those training materials, and we'll be posting the new ones that I'm going to talk about here in a minute on there as well. So to start things off, this is a cover slide for our new introduction and overview training module, which is going to help educate new people to the concepts, the benefits of geothermal equipment, and things that are needed for the system. So this will be the beginning of that training course. And we have a couple examples of the slides that are in that training module that shows some of the things we desire the students to be able to do when they complete it. So after they complete this one, they should be able to explain common terminologies for geothermal heat pump systems. They should be able to also understand the advantages of the geothermal heat pump and provide a simple explanation for how they work, and understand even the differences between a water-to-air unit and a water-to-water geothermal unit. There are various components and supplies needed to complete the installation of an indoor piece of equipment. So we're going to go through those basic components and supplies that would be needed to help people be more familiarized with what it takes to do the indoor equipment, as well as we will be talking about understanding the different types of earth loop connections and methods used to connect them to the earth for heating and cooling the building. And this slide here is an example. Just basically, you're going to tell people, the basic. How does it work? What is it? What is a geothermal system? We kind of call it Geothermal 101. And it's really a mechanical refrigeration system that's employed to create a thermal difference to increase the amount of energy moved in and out of the building or the ground at a higher rate of speed than what the building or ground needs. And so therefore, we're going to mechanically induce the thermal differences to get things going. And there's quite an advantage to doing that with a geothermal heat pump system. So this kind of explains really what it is. It's really just a water-based refrigeration system. And everyone's familiar with the refrigerator analogies of moving heat from hot to cold. We're doing it through the water. Here's one of the slide examples that would give that student in the introduction period, really more background on all the benefits of ground source heat pump and why you would want to use one. Certainly, if you're in the trades as an installer or a service person, people may ask you, and you may not know all the answers about, why someone might want one. Well, we even cover those kind of topics, as you can see on this slide, from the advantages and benefits of using one. And we'll go through that on that training class. We also show some basic, overviews of the main components that are in the building that really compose the geothermal heat pump system up, like the heat pump itself, hose kits, flow center pump systems, some of the fittings that are involved to make connections to do service work, diagnostics, or maintenance on them. So it really is going to be beneficial to, give you a preview before you get into the installation class, knowing what to expect is part of a system, as well as the earth loop connection methods. There are multiple ways to connect a geothermal system to the earth, whether it's a water well system, such as this slide depicts, or a closed loop system where you would use the high density polyethylene plastic pipe that's installed in either a horizontal trenching system or a vertical loop. There are multiple ways to do that, depending on the property and the conditions available and the local cost. So we cover all those methods in general to give people that overview so that they have a better concept about the whole system. This next slide is a cover slide for our new installer training module, and this introduces that and really gets into the installation portion. So if you're a tradesperson or going into installation of heating and air conditioning systems and you need a background on doing specifically geothermal systems, that's what this course is based on helping you with. Just the installation part in the indoor side of the job. The ground loop part many times is done by somebody else, maybe another crew, maybe a subcontracted company. But this training is just for the indoor side of it. So it'll be like setting the unit and all the controls and the piping and the distribution system. So with when you take this course, you should be able to, when you're done, really understand how to properly install that indoor equipment. You should be able to also understand the importance of good ductwork for the indoor unit. Properly size the indoor unit and the water side accessories. So it's a water-based unit, so obviously there's some water fluid piping that's going to be required, so we'll cover all of that. If there's antifreeze systems going to be used on a closed loop system, we'll talk about antifreeze and the requirements for that. Also, we cover the proper tools that are required to do a geothermal installation to fill and purge the fluid system for the closed loop. So if you're doing a closed loop system, so we'll cover those tools as well as even the open loop system. So if you have a water well application and you're not doing closed loop, we always go through that as well. With a geothermal system, you will have the option to do a hot water generator in many cases by the different manufacturers that make them to heat domestic water. And so we go through that option as well, how that's piped and installed and set up, as well as split systems. So many times geothermal is thought of as a packaged unit, but there are split systems available. And those split systems could be all electric geothermal or even a dual fuel system with a fossil fuel backup system, if you will. So we go through those as well as the complete pre-startup, startup, and final checkup of the equipment. So these are all the things that this course is going to cover. And so it's pretty conclusive on the whole gamut of the indoor side of the job. Here's a slide example showing you actually the real details of the training agenda, which is basically tied to those overviews that I just went through. So it's quite broad in what we're going to cover, and just focused on what you as an installer would need to know. Then the next course that we have is our technical service basic training course. And this course is really for the technical people who do service work or maintenance on geothermal systems. So if that's your part of the trade, then this is going to help you with understanding those details that make a geothermal ground source heat pump system a little different from other heat pump technologies or fossil fuel systems. With this course, you can see the slide example. You can see what you should be able to do with that completion of this course. You should be able to properly diagnose and replace flow center pumps, understand pressurization and diagnostics on a closed loop system, understand the tools you need, understand ECM blower motor troubleshooting. Most all of them are using ECM motors today. So there's quite a bit of detail about that in the course, as well as understanding the components used in that refrigeration system. Because this is a water-cooled type refrigeration system, there's a lot of detail on refrigerant circuits and how to diagnose subcooling, superheat on those, as well as measure and verify that your equipment is properly performing. So there's a lot of really good things here that we're going to teach in the technical service basic course. So again, here's the example of the agenda. And it's going to really, I think, be very helpful for if you're in those specific trades, whether an installer or a service person, understanding what you need to know about the actual system. It's not a broad training where they cover all the outdoor stuff with the indoor and all the service. It's kind of a lot of time to do that. And so we've kind of narrowed this up so you can get just what you need for your portion of a job. And whatever training module is most interesting to you, you'll be able to sign up and take. And we think it will be a good thing to do here. So I'm waiting for my slide to change. It's froze up. Not sure why it won't go. Okay, here we go. We'll try the next slide. Hopefully this is projecting yet. So when you complete the courses, we have training course certificates. Like I said, after you take the final exam, there will be a test. So pay attention, take notes. If you have a 70% or better, then you will receive a completion certificate as well as a trainer ID number that you'll be able to carry for your credentials. We will also be bringing out some additional training courses in the coming new year. These will follow after we get these first two real modules done for the installer and the service basic training. We're going to be bringing out Geothermal 101 training. We're going to be doing another course on the outside loop training, as well as one for a designer, doing some design training. So we have a lot of new courses coming. They're going to be kind of job focused, specific, so that if you take work in a particular side of the job, you're going to get just the training that you need in our training modules for that. And on top of that, we do have some existing training courses which ICSPA has been offering, and those would be listed here as the accredited installer, which has been a 3-day comprehensive installation workshop. Once we finalize these new training modules on the residential side, the accredited installer course may eventually go away, because that's such a broad course. We found that 3 days for someone at training sometimes can be a problem. So the modular system is going to be a lot better, probably more focused for a lot of people. So with that whole package, we're going to kind of split it up into what we're talking about today. We do offer the Certified Geo Exchange Designer course, which Ed's going to talk about in a few minutes, which is more comprehensive on the commercial side, anything over maybe 20 tons or larger. That's what that course is really designed for. As well as we have the Certified Geothermal Inspector course, which is a course for those interested maybe in checking out jobs as a quality inspector, or you might work for a local state or county provincial code inspection agency and need to really understand about geothermal systems. This course is tailored for those kind of folks. And then we do offer a train the trainer program for people who would like to train people about the technologies. We even offer a train the trainer course. So on the new courses, when they are rolled out, these are going to be offered in Canada exclusively through the HRAI group, and they are going to be working in the Canadian areas for doing training. And in the U.S., ICSPA will work with the people here in the U.S., but there's trainers already up in the HRI group that are going to be able to do the training courses for you in Canada. So if you'd like to know more about our technology and learn more about systems and network with people, you might consider joining ICSPA, or maybe you've been a past member and let your membership lapse. I think it's time to renew it. And there are a lot of benefits to being an ICSPA member. So certainly we want to remind folks that, to be in the know, if you join our group, it's a good way to stay on top of it. We have a lot of good benefits, as you can see here, for becoming a member. We also are having our annual conference coming up in December out in Las Vegas, which is going to be full of a lot of additional educational seminars. We have a keynote speaker, Alejandro Moreno, who's the Associate Deputy Secretary for the Energy Efficiency and Renewable Energy Office at the DOE here in the U.S. And this conference is going to be out in Las Vegas at the Convention Center, and we're staying at the Wingate or Resorts World Hotels. So are there any questions on the material? You're certainly welcome to ask that, and follow us if you are on social media on any of these media websites. So I'm open for questions if there are any at this point.
All righty, guys. Do we have any questions? This is the time to ask some. All right. We will have another question period at the end. So if anybody has any questions for Greg, we can formulate some questions at that point as well. So you haven't lost it if we start our next presentation as part of this session. Don't go anywhere. So with that, I think we're going to turn it over to Ed then, and we're gonna start his portion. So thanks, Greg. If we need to, we'll touch back at the question period at the end. So Ed, okay. The hot seat's yours.
Great, thanks, Leah. Over my career, I've learned a lot of ways that don't work in this industry, and hopefully the training that ICSPA offers, we can help you avoid the same mistakes that I've made over the years. I'll be talking primarily about small commercial geothermal systems and how some of the differences in the design of a commercial geothermal system compared to a conventional HVAC system. And there are some really fundamental differences that we'll go through. So basically, there's some misperceptions about geothermal systems. First of all, is a lot of people consider them very high cost to build, high capital cost. They're somewhat risky. They don't work as expected, but they do reduce carbon emissions, and that's one of the reasons that the both the Canadian federal government as well as the U.S. federal government have really started pushing on building electrification. These things do provide some big benefits in reducing carbon emissions, and that's becoming a bigger deal as people are starting to realize how much the climate is being impacted. So a quick primer of what a geothermal system is. Basically, what a ground source system does is exchange heat between the building and the earth below it. So the air temperature, as you know, in our climate especially, can range anywhere from -40 to about a plus 110 degrees Fahrenheit, or -40 C to about 40 degrees C or 45 degrees C. That reduces the efficiency of an air source heat pump pretty significantly if we start using the outside air as a heat source or a heat sink. The ground is a much more moderate temperature. In our climate, we're looking at anywhere from about 43, 44 degrees Fahrenheit up to probably about 55 degrees Fahrenheit across Canada. And that's a much more moderate heat source and heat sink than the air source. The way we move that energy back and forth is basically bury a bunch of plastic pipe in the ground in vertical boreholes, horizontal excavations, horizontal drills, surface water, and that kind of thing. There's a lot of different ways of transferring energy back and forth, but fundamentally we're circulating fluid through the pipe that we bury in the dirt, circulate through a heat pump, and all the heat pump does is either warm the fluid when we're air conditioning with that heat pump, takes the heat from the building, dumps it into the water, warms it up, creates a temperature difference between the fluid in the ground and the fluid and the ground around it, and transfers energy. And vice versa, when we're extracting heat from it, we're cooling that fluid and moving that heat into the building. A lot of different ways of transferring energy back and forth. Vertical boreholes is probably more common, especially in vertical loops, but horizontal excavations, if you've got a school that you're looking at, most schoolyards would have enough space to install a horizontal ground loop. Horizontal drilling is another variation of that. If you happen to be near a body of water, whether it's the ocean or the lakes or whatever, that can be used as a heat source as well. And if you have access to a good aquifer under the building, that can provide heating and cooling as well. There's also more and more interest in taking heat directly from structures that we're building, whether it's piles under a building, basically bury a plastic pipe in there. Photograph on the left shows a pipe being installed in piles under a building in downtown New York, in Manhattan. There's a quarter million square foot building connected to these piles, and just the pipe in the piles provides about 40% of the heating and about 30% of the cooling for that building, and that is supplemented by an air source heat pump. Systems have been installed, pipes have been installed in subway tunnels or in wastewater pipes, a lot of different ways. As long as you can contact the dirt with the pipe, you can transfer energy. And as I said earlier, one of the biggest benefits is that we're working with much more moderate temperatures. If you look at the dark green line here, that's the typical temperature range that you would see in a ground source heat pump in a residential or small commercial application, anywhere from about just around freezing point up to about maybe 70 or 80 degrees, whereas the air temperature might get up to 100, 110 degrees or down to -30 or -40. We've got a much more moderate temperature, and that's where the efficiency of the heat pump comes from. So I'd mentioned some of the differences between designing a conventional system versus a ground source heat pump system. There are some very, very fundamental differences. If you're connected to a gas pipeline or an electric grid or an oil delivery service, you've got basically an infinite source of energy. As long as you're paying the utility or the delivery service, you've got energy. Doesn't matter how much you're using. Doesn't matter how much you're running that boiler or furnace. Somebody is going to shove energy down that pipeline. Same with the cooling tower. If you've got connected to a water utility, you're paying for the water, and you've got an infinite source of water, and the wind is going to blow away any heat that you're taking from the building. So when you're designing a conventional system, you've got an basically you can select the energy source and the heat sink basically from a manufacturer's catalog. These are designed basically, if you know what the weather data is that you're working with, you can select a cooling tower quite simply. You only need to know how many BTUs you have to get rid of. Same with the gas pipeline. If you're connecting to a gas pipeline, you've got an infinite source of energy. As long as you're paying the bill, all you need to know is how many BTUs you have to deliver to that equipment on the worst day of the year. And that's the extent that you have to worry about the energy source. Ground source system is different. Basically, what you're doing is building an energy storage tank in the ground. And the ground itself is not really a great conductor of heat, but if you install enough pipe in there and you circulate fluid through it, you change the temperature of that fluid, you can move that energy around. You're going to gradually, by the end of the year, at the end of the summer, you're going to warm up that fluid probably to around 80 to 90, 95 degrees Fahrenheit. And that's the high maximum temperature that most water source heat pumps are comfortable operating at a reasonable efficiency. If it's a cooler temperature that you're working with, the heat pump is going to work more efficiently. So you're starting with a ground temperature in Canada about 45 to 55 degrees. You're going to warm up the dirt around the pipe up to about 85 or 95 degrees by the end of summer. The opposite happens in the winter when you're extracting heat from the dirt. You've got the same base temperature to start with. When you're starting up the system basically in fall time to heat the building, you're going to have warmer temperatures to start with because of all the heat that you've dumped in there all summer long. By the end of the winter, you're going to get down to about 30 to 40 degrees Fahrenheit. And again, that's where heat pumps are comfortable operating at. If you drop it down to 20 or 15 degrees Fahrenheit, the heat pumps are going to quit working. So the key is designing the system, the ground heat exchanger, so that it's going to provide those temperatures throughout the year. In HVAC system design, you can get away with rules of thumb to estimate what the size of the equipment is. One common rule of thumb that I've heard over and over again is about 400 square feet of building per ton of equipment. And that's a fairly common rule of thumb, especially for commercial buildings. Another rule of thumb that's often used in the industry, and this varies a little bit from one region to another, but 180 to 200 to 220 feet of borehole per ton of equipment that you've installed in the building. And that's often used when a building owner comes to a designer and asks, is it feasible to install a geothermal system in my building? And for a quick number, this is often the kind of numbers that are used. The problem is that the size and the cost and the performance of a ground heat exchanger is very site and building specific. Rules of thumb don't really apply to these systems. And as an example, if we were looking at 3 buildings, church, retail store, and an apartment building, they may all have exactly the same peak heating and cooling loads, 140 kilowatts or 480,000 BTUs per hour or 40 tons of cooling, 113 kilowatts or 385,000 BTUs per hour in heating. These loads might be identical. And if you applied those rules of thumb, 40 tons times 200 feet per ton, the rules of thumb would suggest you need about 8,000 feet of drilling. But what's missing is the number of hours that system is going to run to cool this building, or this building, or this building, church, retail store, and apartment building. This one's going to run a lot fewer hours in cooling because it's only used a few times a week. This one is going to be running a lot more hours because that store might be open for 12, 14, 16, 18 hours a day. And there's a lot of people running around in the store, lights on, so it's going to force that same 40 tons to run a lot more often. And the apartment is probably somewhere in between, just about right. Even though the peak loads are identical on all 3s, the energy loads are quite a bit different. So if we look at this, 480,000 BTUs, 385, they're identical. This one's much bigger than in the amount of heat that we're extracting from the dirt, than how much heat we're dumping back into it. This one is exactly the opposite. This one's somewhere in between. So what that means is that if you're looking at the peak loads and designing your system based on that, and I'm saying designing in quotation marks, it doesn't really reflect how much energy you're dumping into the ground or pulling from it. This is how much heat you're dumping into the ground from the church, the retail store, and the apartment. This is how much heat you're extracting. And that difference is pretty significant. And it gets even worse because the compressor energy that the power electricity that you're using to power the compressors and pumps, that's going to go into the ground heat when you're air conditioning. The compressor is cooled by the refrigerant. That heat is going to be dumped into the ground, and it's also going to supply some of the heat to that building when you're heating that building. So you're extracting less heat from the ground than you're delivering to the building. You're dumping more heat into the ground than you're taking from the building. So what that means what the temperatures of the ground loop are going to do over the years, this one's eventually going to get too cold because you're extracting more heat from the ground than you're putting in. This one's going to do exactly the opposite. It's going to get too warm. This one's going to be just right, going to be well within the good, efficient operating ranges of that heat pump. Over time, over 10 years, this one's going to drop in temperature. This one's going to increase in temperature to the point where the heat pumps aren't going to operate efficiently. And this last one is going to stay within that same efficient operating range for the life of the building. Installing more pipe in the ground, all that's going to do is delay the inevitable, in this case, cooling of the ground. Even though you've got a larger ground loop, it's going to take a little bit longer to cool off too much. Even if you're looking at 11,000 feet of drilling instead of 8,000, it's going to eventually get to the point where it's too cold. Same thing in the retail store. Even if you increase the size from 8,000 up to 13,000 feet of drilling, this is eventually going to get too warm. Whereas this one can continue on sustainably for the life of the building, because the energy loads, how much heat you're putting into the ground versus how much you're taking out, is going to be fairly even throughout the life of the building. So this one's bigger, this one's bigger, this one's bigger because we're extracting more heat. This one's bigger because we're dumping more heat into it. This one's going to be smaller because we're dumping into the ground, we're taking out the following year. And that means a smaller, less expensive ground loop, which is going to be a lot more cost effective to build. So rules of thumb don't really apply to this industry. And the key is really balancing how much energy you're shoving into the ground versus how much you're taking out. So where do you start when you want to have a client that wants a ground source heat pump system? As an example, this is about a 22,800 square foot, 19 unit apartment building, ASHRAE Climate Zone 5, similar to Toronto. Then a couple of other iterations. The initial energy model was built based on standard building codes, ASHRAE 90.1, and several different iterations of that energy model were built. What happens if you improve the glass, change the solar heat gain coefficient, how much solar gain you're going to get coming into that window, or how much you're going to block out, and what the U value is, what the insulation level is of that glass. What happens if you add an energy recovery ventilation system to that system and recover the energy from the exhaust air? It's going to reduce the loads in heating. It's going to reduce the loads in cooling. If you combine both of these things, you can get fairly close to balancing loads in that building. So the design methodology really needs to be much different, because you really have to look at, ideally, what you can do with the building by working with the mechanical system designer, with the architect, and with the building owner. What can you do to that building that would make the energy loads that you're going to shove into the ground versus taking out work more efficiently? So a lot of different things: how much glass you're putting on the building, what kind of glass you're putting on the building, how you're shading that glass. Are you taking advantage of the light to cool it, the outdoor light to light the building instead of using electric lights to do that? Same thing with a mechanical system, a heat energy recovery ventilation system. You might look at what the efficiency of the boilers are, how you're distributing that heat. If you're looking at 65-degree chilled water through the chilled beams, or 80-degree water through radiant floor systems, and what kind of pumping systems, all of those things have an impact on how much heat you're dumping into the ground versus how much you're taking out. So as an example, you can see the energy load profile. Here's how much energy that this particular building is using, 23,000 square foot building. Here's what that looks like for peak heating loads, peak cooling loads, annual heating requirements, and annual cooling requirements. So if we change the glass on there, that changes the loads a little bit. Here we're looking at 22 tons. We've knocked the ton off there, and it changes the loads a little bit, and it changes the energy balance. If we add an energy recovery ventilation system, now we're down to 17 tons of heating, and the cooling stays about the same, so it changes the energy balance on it. Add both of those efficiency measures, that changes it again. And it's a really building specific kind of a technology. Look at unique features of a given building that might help to balance the energy loads. What that does to the size of the ground loop, if we're looking at ASHRAE 90.1 building, standard building, built in Model National Energy Code, changing the glass on here doesn't make much of an impact. It would make a much bigger difference if you had a lot of glass on that building. Adding the energy recovery ventilation system, now we're knocked about 25 or 25% off the size of the ground heat exchanger. Instead of, and that can be a pretty big deal. If you're looking at 8,000 feet of drilling times, let's say $30 a foot, that's a big deal. 240,000 bucks. Now we're down to 180,000 bucks. Knock it off a little bit farther when you add both of these components. What happens if we look at the design of that ground heat exchanger itself? Changing the borehole space. Borehole design, putting thermally enhanced grout in there so you can transfer heat more quickly than you can with a standard grout that's installed. So now we're looking at a 50% reduction in the size and the cost of the ground heat exchanger. That's going to be the difference between a 5 and 6 or 7 year simple payback versus a 15 or 20 year simple payback. Which one is the client most likely to buy? And what's even more interesting is that this one cools off less over time than a borehole field that's much larger. So you're looking at knocking off 4,000 feet of drilling times, let's say $30 a foot, 120,000 bucks, and you can buy a lot of window and a lot of energy recovery ventilation system for a 23,000 square foot building for that kind of thing. So those are the kinds of trade-offs that we're looking for when we're designing a geothermal system. And then once you've got the system installed in the building, if you think about an electric utility or a gas utility, they need to know how much gas to shove down the pipeline or how many electrons to shove down the wires on any given day. They need to have the generating capacity to that. So when a big city is getting really, really hot by the end of summer, in the afternoon, how many kilowatts do they have to deliver to that city? And those are the kinds of calculations that you have to do. You're basically building a utility when you're looking at building the ground heat exchanger. And you can be sure that the electric and gas utilities are monitoring how much energy that there is being used from their system, and they're going to adjust the system accordingly. You can do exactly the same thing with a ground heat exchanger. So what I'm suggesting is that if you are careful with the design of the system and looking at analyzing the system, what the energy needs are for that building, you're going to get a much better return on your investment. It's going to reduce or eliminate the risk of operating that geothermal system. And you're still going to get the CO2 emissions reductions that the client and everybody seems to be looking for these days. And these things can work virtually anywhere. I have designed systems in Kerala, India, where the ground temperature is 82 degrees. And the energy modeling software that we used basically asked, are you serious that there's no heating load in this building at all, period? The winter design temperature in that location was 22 degrees C. There is no heating requirement, period. And have also designed systems in Anadyr, Russia, in Siberia, to maintain the permafrost under an aircraft hangar. So those are the kinds of things you can do with these kinds of systems, and in a lot of cases, it's more cost effective. They can certainly become a lot more cost effective to build and provide the energy cost savings that the client is looking for. So basically, this is a really, really quick overview of the Certified GeoExchange Designer course that IGSHP presents. The design course is 10 live sessions, about 75 to 90 minutes long each. Typically, it's presented one lunch hour per week for 10 weeks. I've got one that I started about 2 weeks ago. It'll finish up at the IGSPA conference in Las Vegas. And it's you get accreditation from the Association of Energy Engineers. If you are looking for more information about it, if you visit the IGSPA website for the information of about what the Certified Geoexchange Designer course is, or how to register for it, it's all on the site. So again, they're open to questions both for Greg and for myself. Happy to try and answer them as best we can.
Wonderful. Thanks so much, Ed. Do we have any questions from the audience? I know there's some of you guys still there. Come on, let's ask some questions.
Don't be shy.
I think I see 15 people in the audience. Is that right, Leah?
No, there's 32 of them.
Oh, 32. Okay.
There's 32 of them.
Cool.
And they're all too shy to ask a question.
Apparently.
I'm sure as contractors, some of you occasionally get asked for, is it feasible to install a geothermal system in my small office building or whatever, or your church or whatever? Or you work with mechanical system designers that haven't had much experience and don't know where to turn. There are places where you can get that kind of information.
All right, guys, we got 14 minutes. Any questions, guys? We have some two great experts here joining us today. So.
We're fishing.
Yeah, we are.
One thing that we are starting to see around across North America, including in Canada and the US, that even gas utilities are starting to install geothermal systems. Enbridge Gas is starting to do that. Eversource Energy in Massachusetts and National Grid are starting to install geothermal systems. Otter Tail Power in Minnesota, same thing.
We have 3 gas utilities that have joined IGSPA as members now. So this is the new energy transition, and we were part of it. And you as technicians in the trade are going to also be in that. So, this is a place to get your questions answered and get involved, because it's going to be a great career path as we go forward. I mean, Ed and me have been at it a long time, 20, 30, 40 years. And it's never boring and lots of fun.
Well, we do actually have one question in. So Eric, you're awesome. Oh, and Dana, we also have another one. You guys are great. Thank you for coming in with some questions. So I'm going to go with Eric's first because he was first, and then we'll go to the next one. So the first one is, how can we get the cost overall for geothermal installs to lower?
The best way to do that is by really understanding how much energy that building needs for heating and how much it needs for cooling. And then if you have the opportunity to work with the owner, the architect, the mechanical designer, you can change those building heating and cooling loads. And the best way I've found to do that is to try and get a balance on how much energy you're trying to shove into the ground versus how much you're trying to extract.
Do you think rebates will be also an important part of trying to increase the adoption of ground source heat pumps?
The only problem I have with rebates is that they sometimes, unless there's some accountability to it, and I've seen that both in Canada and the US, is that the systems are not, there's nobody being accountable for the design of those systems. They're just putting in a whole bunch of equipment and getting a whole bunch of money for it for doing nothing. And it enables, in some cases, bad design.
Okay. All right. And then our other question we have here is, do the training for ground source heat pumps aligns with CSA C448 standard?
Yes, it does.
It does.
Okay.
Yep. Yeah, one of the things on the cost question, because cost always comes up, people want to know what they can do to lower their costs so they can buy geothermal and put it in. It's just what Ed's talking about in his course, is that course helps you understand that there are trade-offs in the building design if the building owner, like Ed said, are willing and open to consider some different changes that could accommodate the geothermal at a lower cost. You got to do some trade-offs. Sometimes, the shading of the windows and orientations and use of the building can matter. So we have some good things and tools that can be used to help that. And people that don't have it just only know one way to quote it and say, sell it. And what we offer are some tools that expand your knowledge so that you know a lot of options that you could talk with them about considering, which may make it very viable. And I think, the rebates certainly help. I think it's probably gotten them down to where it's pretty affordable for most commercial building owners, even now, where it's like, 7 years? And where it used to be a 10, 15, 20-year payback or longer. We've shortened that up by the use of the rebates today and the incentives that the governments are putting out there. So it's never been a better time to propose it and sell it and do it, but you have to be smarter about it if you want to sell more of them, and you want to do it without the risk. So that's kind of the things that Ed was talking about.
Okay, we actually do have a couple more questions. So thanks, guys, for pulling in some questions. I appreciate it. So we have another one here. How often should the glycol loops be tested for flow?
I've had my system in my house since 1992. I've got a mixture of methanol and 15% methanol in water. Probably about 7 or 8 years ago, I changed the heat pump from what I had originally, installed the new one, left the same fluid in there, and it's been going fine since. So that's 31 years.
Wow.
They should check the system on an annual maintenance, service check, but you don't have to necessarily replace it or do much with it. As long as it stays sealed, it's like water in a bottle. It just keeps recirculating round and round. And if you don't have a loss, you don't have makeups or dilutions to affect your antifreeze and fluid solution.
Awesome. Thank you, guys. So we have another one that's pulled in. So we have one. Have you ever seen a water to air unit with natural gas backup?
My system has no backup, period. You could do a system with a gas backup. Generally, it's not the best thing you could do, basically, because the cooling coil on the gas, if you're putting a cooling coil with a split system heat pump with a cooling coil sitting above a gas furnace, you can potentially get the dripping onto the heat exchanger, rot out the heat exchanger on the gas furnace. And the gas furnace typically is going to produce warm air at, depending on how it's sized, at probably 110, 120, 130 degrees. And that's generally higher temperature than you want to produce with a ground source heat pump. So it's probably not the best idea in the world. And you have to put the gas furnace in ahead of the air coil. In most cases, correct me if I'm wrong on that, Greg, but I think that's still the way it is. With electric auxiliary that is available from most manufacturers, that electric coil is downstream of where the heat pump is, and it only is used as it's needed.
That's correct. I think the furnace manufacturers don't want the coil before the heat exchanger. They want it after, so it doesn't cause as much problems with them. But certainly dual fuel in a residential application has been done quite often, especially if people have a marginal electrical service panel to their home, and maybe they don't have enough power to run a lot of electric backup with the heat pump. You could use a dual fuel system like that to augment the system that way. But with economies today in most places, going with one electric bill instead of 2 utility bills is always very attractive.
Well, there are some areas too you can't run natural gas lines to them.
That's right.
Too, right? So
now moratoriums starting to start up in different places where you can't get gas.
Mm-hmm. I know
the other thing to consider.
Sorry, go ahead.
Yeah, the other thing to consider across Canada is that with the carbon tax, whether you agree with the carbon tax or not, at this point it's a fact of life, and it's going to double the price of gas in Canada in the next 5 years.
Yeah, so only more encouragement towards electrification. All right. Do we have any more questions from the attendees? There's now 39 of you, so there's lots of you guys to ask some questions right now.
Awesome.
All righty.
I'll be happy to respond to emails or phone calls if you like.
Yes.
Same here.
See it on screen.
Wonderful.
For sure.
Okay, if any other questions come up while I'm talking, I'll make sure to jump into them, but I will do my little wrap up now. So thanks both Ed and Greg for your presentations today. They've been fantastic. Thanks everyone for joining in. We do have another speed meeting, so hopefully everyone enjoyed the first one. You have another opportunity to go in again. Otherwise, we have 2 more presentations to go for the day. So we have Steve presenting on navigating grant incentives for heat pumps, so kind of related to some of the things we've talked about in the question period today. And then also we have Trevor Matthews presenting on understanding CO2 heat pumps. So thanks again, everybody. Thanks, Ed and Greg. Wonderful presentation. And hopefully you guys can join in on the speed meetings. All righty.
Sounds good.
Thank you, guys.
Thanks, Leah.